Hello everyone, this is our second week of data science software and experiments. Today, let's talk about the homework first. This is our first homework assignment. For this homework assignment, you will use numpy to create feature images. The text will be released on E3 platform, and because this is your first homework assignment, you will have 2 weeks to complete it, including like setting up the environment and maybe prepare some preliminary knowledge that might be helpful for this class. So you'll have 2 weeks to do these homeworks. Details will be available on E3 platform. So first of all, be sure to take a look at the examples we have provided. On this page, you can see that there are 2 examples are provided that is made by myself in previous years as an example for this class. You can see that if you click into the Colab notebooks, you can see that it is in fact image generator that has several controls so that you can change the colors of the hair or the size of the eyes or the position of the mouse, etc. This is just 2 similar examples. In previous years, students having been very creative and have a lot of imagination on these homeworks. So they did a lot of great job. I can give you a quick glance of what the students in previous years has done. This is a simple collection of one, I think it's 2018 class. So you can see that this is something you can actually draw from scratch using numpy alone. Okay, this is just a quick view of what you can do. So that give you some ideas what you are going to do in this homework assignment. You may find a little bit challenging at first glance, but don't worry about it. In this class video lectures, we are going to cover everything you need to know to complete this assignment. So you have a template. You're going to use numpy functionalities to actually realize your imagination. So throughout this lesson, we'll discuss many concepts related to this homework. This assignment serves as several purposes. First, it can help you to visualize how numpy works, because numpy is kind of abstract tools that works on an array, which is also abstract ideas. But by using an image to visualize what inside the numpy array, it helps you to understand and the visualization of what the numpy operations or numpy functions works on these arrays. Okay, so secondly, because many of you have different level of experience of numpy. Some of you may have some experience of numpy, and some of you may be new to Python or numpy. So if I just go through all the numpy functions, it might be a little bit boring for people who already know a lot of numpy. However, because our application is not exactly the typical way of using numpy library, so even if you are kind of familiar with numpy functions, since maybe still a little bit challenging or something you haven't seen before, the functionalities and the things I'm going to show you may be still kind of new to you. So everyone can take something from this lecture. Okay, just note that in general, typically if we wish to draw something, numpy array is still very common format for an image. If you wish to do computer visions like in OpenCV or in Scikit-image or in other applications, numpy array is still a very typical format to represent images. It's just that when we wish to draw something on these images, we usually use other libraries like Pillow or maybe OpenCV, maybe other libraries, but OpenCV and Pillow, PIL, both of them provides a very complete set of tools that can draw things an image, like drawing a path, drawing a polygon, drawing a circle, or filling something, etc. So what we are going to learn is not very going to be useful. It just serves as a tools for you to learn the foundation and the basics of numpy. So the key takeaway is to focus on solving problem using numpy rather than just learning NumPy itself. So we're using this drawing things, drawing image things as our focus problem that we wish to solve. And by solving it using NumPy, which is not a thing that you're going to use after this class. You're going to use Pillow or OpenCV or drawing libraries to do so. But by using NumPy to draw something on this image, you're going to learn things from NumPy. So by solving this problem, you're going to learn NumPy itself. So this is the approach I want to emphasize in your learnings, because I think this is the right way to learn. When you focus on solving problem instead of learning things, you are focusing on solving problem. You'll find that NumPy offers many useful tools to help you to get there, to solve your problem. So you actually get a chance to like the things you are going to learn. However, if your mindset is solely on learning a things like learning NumPy, then because NumPy has a lot of different functionality, a lot of tools, they are becoming something that the obstacle or difficulty that you are going to overcome, and you are going to feel overwhelming. You will feel like, okay, why does NumPy need to have so much functionality, so much function? I don't have time to learn so much things. However, on the other way, if you are focusing on solving a problem, you will think like, okay, that's cool. NumPy has so many tools available that I can use to solve a problem. So you see, that's a two different kind of mindset, and it makes a lot of difference when you try to learn things. So don't focus on learning things, focusing on a problem that you would like to solve. And by solving this problem, on the way of solving this problem, you're going to learn a lot of things from, in this case, learn a lot of functionalities that is useful for you in NumPy. So drawing something is a thing that most people enjoy. So don't worry about anything else, just focusing on creating something interesting. Just enjoy the process, and you will naturally remember the functions of NumPy. So in contrast to focusing on learning the NumPy functionality, like reading a dictionary or reading a textbook, just focusing solving a problem, you are going to remember things along the way when you're solving the problem. You are going to actually remember these functionalities because they are part of your journey. It's not just some textbook materials that you have a very hard time to remember them. Okay, so I have to note that if you have some special conditions or situations, please just let me know, because I have taught for quite a long time. I do encounter many students have different background and situations. For example, I previously had one student that is visually impaired, not in this class, not in data science software class, but in another one, who need to enlarge the paper when he takes the examinations. He can still see something, but it requires to be enlarged. So in the midterm and in the final, we have to allow him to have some tools like computers or a tablet like iPad, so that he can use it to enlarge part of the paper. So we can also provide different version, different edition of the problem set, so that every text is large enough, but they prefer to bring their own tools because they are familiar with the tools they have. If we print out just enlarge the text in a question, they may not be big enough or just being too big. So they prefer that he use the laptop or other tools to magnify the text on the paper. So I understand that people may have different needs and different situations. I can imagine in some case, you just hate drawing things. That is very possible. So because there are so many different kind of situations, just to be careful and just to be sure that to help everybody just enjoy solving a problem. That's my main point. You have to solving one problem along the way. But if this is the case that drawing is not your thing, maybe because some visually impaired or other reasons, just let me know, and I can adjust the homework assignment, and so that we can take a different approach. So the same apply to all of the future assignments. Or in a lecture, if you have different needs, just let me know. So now let's move on the course content itself. So let's continue to study NumPy using our notebook. So you can find the notebook in our GitHub repo. So you can see here is a link to a repo, and in 01 NumPy, then you can find the notebook. I'm opening this notebook in Visual Studio Code, but they are pretty much the same. Okay, so last week we summarized how to create a NumPy array. We talked about a few ways to visualize a NumPy array. And finally, we summarize when you learn some new concept. We itemize, list, enumerate several items that you can consider about what this object or what this library is. So one thing we need to know about this object is what kind of function or operations can we use with this object. In our case, the object is an array, an empty array. The most simple and the most common operation on a NumPy empty array is element-wise operation. You can see right here, element-wise operations. So for example, we have already seen that when given a NumPy array like 1, 2, 3, 4, and we can multiply it by 4. And when we multiply an array by 4, we mean we multiply each element with the number 4. So 1 times 4 is equal to 4, 2 times 4 is equal to 8, 3 times 4 is equal to 12, 4 times 4 is equal to 16. And not only you can do the multiplication, you can also do the addition. We can sum 3 with it. Similarly, if you have two arrays, we also have element-wise operations. Like suppose we have an array called x is equal to 1, 2, 3, 4, and say y is equal to, let's make it a bit interesting, like 4, 3, 2, 1. So what does it mean by x times y? I mean m at y. We sum x and y up, then we do it element by element. That is exactly what element-wise means. Let me elaborate using the following example. By using the sign function. So from the standard library of Python, we can have a sign function and we can get the number pi. So for example, let me import pi, and we can see the value of pi is 3.14159, and we can use sign function on pi. What is the value of sign pi? It is 0. And what so you may see that this is not a 0, but it is very small number, because we're using floating numbers. Floating number is not that accurate, so this is something that we can live with. But you can see that it is close enough because this is a very, very small number. So let's do another quick check. To sine pi over 2, it should be 1, and in fact we get a 1. So what about let's try sine over 4? It should be like a square root of 2. In fact, it's 1 over 2. The square of it is 1 over 2, so it's a square root of 1 over 2. So this is a sign function, and we already know that how it apply to the sign function applying to a number. But what does it mean by applying this sign function to an array or to a vector or to a metric. There are different meanings, but in numpy, if we can apply this sign function to numbers, and the numbers are the elements of an array, so the semantic of sign on an array is simply we apply this function to each of the element and replace the result, replace the output, replace the value with its output. So let's see. Say we have construct a lot of different points between 0 and pi over 2. We can also use np.pi to get the value pi instead of use mass.pi because numpy has its set of all constant. So you don't have to import other libraries. You can import numpy alone. You will get everything. So first of all, we get all values, 91 equal distance values between 0 and pi over 2. And we can apply this sign function to each of the values, each of the element in X, and we get all the result. We can use matplotlib to plot the result so that you can see it should coincide with the sign function, the curve of sign function that we're familiar with. Let's see. You can get this. So this is from 0 to 2 pi. So we get like 1000 points. Actually 1001 points between 0 and pi over 2. I mean 2 pi, including both ends. So by plotting the result using like the x as the x-axis and the sine x as the y-axis, then we get this sine curve. Also, you can see that it illustrates that one of the very convenient way of using numpy, because it actually looks like a symbolic notations of sine x. If you because we usually treat x as a symbol, as a variable in mathematics, so that we sometimes we write y equals to sine x, so that y is in fact the values of mapping x using sine function. So sine x is sometimes equivalent of saying the sine function itself by taking x as the input. So it looks like the mathematics notations, and it can be used sometimes like a mathematical notation. So we got the curve of sine function. It's just that everything is simply arrays. So x is an array that takes 1000 plus 1 element, and if we let y equals to np sine x, then y itself is an array. It takes memory to store these things, and so you can see that it has 1001 element, 1001 element, and the d type should be float 64. So it takes memory to store these values, and you're not getting the infinite precision. We only compute those 1001 elements. But because we get enough elements, like we cannot actually tell the difference. It should be a piecewise linear graph, but we cannot tell the difference. So it looks like we are doing it symbolically. And 1001 element is not a big deal in today's computer. So sometimes you can use numpy very easily, just like what you can do with your mathematics object. Just sometimes. Okay, so we have a hands-on question here, is to try to plot and graph this y equals to x squared plus 1. You can do for other functions, but this is just a hands-on lab, so that you can try if you understand everything correctly. So if it is your first time to encounter NumPy, it might be a good way to try this experience on this notebook. Try to control some function. So here is y squared plus 1. Try to control this function and plot the results. So in this case, you can see we have already a solution. So sometimes you don't get. In previous class, I have provided some solution in the repo. Currently, it is not available on the repo, but I will get this solution pushed on the repo, so you can check these solutions. So this simple quest or simple lab is not like a test or examination. It's just simply a checkpoint for you, so that you can make sure you understand everything. So just try this example, and feel free to change things. Like you can change it to a cubic function. So maybe I can simply add some cubic function right here. Like let me just call it z. Z is equal to x, like square cubic, and x minus. Let me put it like a minus x square minus x plus 1, something like this one. And I can plot it. Let me make it a little bit smaller, because my range is from -3 to 3. So let me make it like 0.1 times 8. So so what is my? I can actually put a legend. Here, and this one should be z, because I don't know what my z is. Maybe it's just no. Let me should be label. So sometimes it is very common that you will face something. You get some errors here and there. But right now I can see that my z is something look like this one. Maybe I should just, because my goal is try to have a cubic-like function. So you know what a cubic-like function is? Just go up and down and up. And so I'm trying to do some experiments here and there to get my function. So maybe I can just do something like this one. This looks a little bit better. Maybe I can make it like times 3, and move it up a little bit. So it looks better. It looks more like a cubic function. I can actually tweak it around like here, like 3 times this guy. It makes it more cubic-like. Or maybe I can actually put this guy into a plus and see what happens. Doesn't change a lot, but you can see that this is a playground that you can play with it and to see construct any function you like. You can feel free to try other functions. For example, maybe you can try just something like exponential. So you don't have to ask what does it mean. by exponential. We have never told you what is NP exponential works on an array. What does it even mean? Do we need a Taylor series or Taylor expansion for it? No, it just applies element wisely. You learn one thing, you just learn a sign function. You learn everything. So just put this one, you can see what is our Z looks like this one. But why does it look like this one? Okay, I do something really strange. I first compute this QP function for Z, and I substitute this Z as input into an exponential function. That's why I get this strange function right here. So that's interesting, but you can try everything. Okay, just to summarize, there are two types of element-wise operations. At least for now, there are two types of element-wise operations. One is something like, okay, we have a, let's just say that 1, 2, 3 plus 4 plus 5 here. So this guy, we apply this guy to each of the elements. And the other type of thing you might see is that, like we have done, like x times that x is equal to an array right here, and y is equal to an array like this guy, and we can do this one. This element-wise means 1 plus 4, 2 plus 3, 3 plus 2, and 4 plus 1. So these two type of element-wise operations is a little bit different. There are some apparent differences between these two examples. For one, that this example, we have two arrays involved, and for this example, it has only one array involved. Kind of like the example like using the sign function, like np.sign for np.array1. So in this case, it also has just one array involved with these operations. So although all these element-wise operations are kind of obvious or trivial to understand, or at least it's kind of easy to understand, but they are some more fundamentally different. So for one thing, let's consider the last two examples. These two examples demonstrate the different type of operations. So for the first one, a sign function takes only one input. So if we treat it as an operator, it is just a unitary operation. It is a unitary operator because it takes only one input. So in this case, it is quite easy. We just apply this function on each of element. But for the second one, the addition or like the multiplication, they are binary operators. They take two inputs, two values as input. So in this case, we in a more strict sense, we need two arrays that has equal size. So we can pair one element from the first array to an element to the second array, position wisely. So in this way, we can take pairs of elements and let them to be the input of these binary operators. However, in this case, we still use the addition as our operation, but there's only one arrays involved. The other part is only a number, although it still seems to be pretty trivial. But this kind of things is something we call the broadcast. So we can actually do this sort of element-wise operation on some type of arrays that does not have the same size. You can treat that 5 as an array. It has a different size. It only has one element. You can treat it like this one. If you think, in fact, you can actually do these things. This one still works. The reason that it works is because we have a rule called broadcast. So we will talk about it a little bit later. But just so you know, there are some fundamental principle behind them. You don't need to worry too much about it. It comes to time that you are going to need to understand the broadcast behavior. But it is not now, so we'll wait when we need it to explain it. Also, there's a very interesting small command called the load. This type of command is called the Jupyter Notebook or IPython Notebook metric function. By using this load metric function, you can load a Python file into, or any text file for what we concern, any files into a cell. It is very convenient, at least for our case. If you want to see the solution that I provided, so you can simply load the q0.py and you can see my reference solution to this small hands-on task. So here goes another small hands-on task, Q1. I call it quiz 1. So we got a quiz 0 and this one's a quiz 1. So from quiz 1, we are going to investigate the numpy functionalities by treating a numpy array as an image. Quiz number 1 is directly related to our homework because it basically shows how to open an image and convert the image into a numpy array and convert the numpy array back to an image and then display it on the notebook. So I strongly recommend that you encourage you to try it by yourself, so that serve as a checkpoint so that you understand everything. So here is a quick example running it. So you can see in this code, first we import the pillow function. From pillow we import the image, and using the pillow function to open an image that exists in our repo. You probably have to update your the repo to pull the repo, because I updated the repo recently. So if you haven't updated the repo yet, you probably won't find the file. But even so, even if you don't have this image available, or if you don't want to use this image, you want to use another image instead, you can feel free to change the path of the image and put it right here. Load the image. You may encounter some issues because especially if you are using Windows as your develop environment. Windows has use a different character. Use the slash as the separator for the path. So you may encounter some troubles when you use it on Windows. So, but this is not in our scope to handle the string or the path. So you can try it, and if you encounter any issue, try to overcome it. But for this checkpoint, try to load some image in your computer, and you can see you should see the image rendered in your notebook, just like here. Plus, you should check the shape and the detail of the array that converted from the image. Just like we have mentioned in last week, when you construct a new array, a new ND array, it is always a good idea to check the shape and the detail so that you have a basic idea of what the array is, and then you should have checked the content. In this case, the shape of the array is 530 and 804. The 530 is the height of the image. So the height of the image is 530, and the width of the image is 800. So what about this 4? Usually you get a 4 or 3 on the last element of the shape. When it is 3, then it is RGB. It usually represents RGB, which means red, green, and blue. So we have 3 different channels or layers of each of the color. And when it comes with the 4 right here at the end, it usually stands for RGBA. So in addition to the red, green, blue, it also have alpha channel that represent the opacity of this image, which means you can use it to determine whether it is transparent or each pixel. Determine for each pixel how transparent that pixel is. And the D type is uint8, which means unsigned integer of 8-bit. That means the value of each element is start from 0 to 255. So that is the range of uint8 D type. Okay, so we already know that the image content can be represented by an ND array. So we can do it backward. We can construct ND array and show and convert the array to an image so that we can see the content, see the values inside the array. So for example, let's construct a simple array, which is just like this one. So you can see that each of this one is represent a color like 25500, because we are trying to construct an RGB image that has only 3 channels. So 25500 means it is a pure red. And for this guy, this one is a gray, because we have 127, 127, 127. It's somewhere in between, in the middle of a range of each color channel. So it is a gray color. And for here, it should be a pure green. And for this guy, it should be a pure blue, because it has the maximum value on the blue channel and 0 on the other channels, red and green channels. So let's see what this X is. It has a shape of 223. The first one, recall the first one is the height of the image, and the second one is the width of the image, and the third one means it has 3 channels, RGB 3 channels. So we can show this image, because if we simply converted it into an image, we can still see this guy, but it is just too small. You can use, if you are using Visual Studio Code, you can use these tools to actually explore this guy by maybe, but this one is just too small. Cannot do much things about this one. But usually you can navigate this image by zooming in, zooming out. However, we only have like 4 pixels, 2 by 2, 4 pixels. So I cannot do much about this thing. It just give you evidence that we have already shown this image. It's just this image is too small. So maybe we should resize it to a bigger image so that we can view it better. So I resize this image to 200 by 200. Because I don't want to interpolate the colors too much. So I want to see it like the color as it would. I do not want the color to be mixed up. So I use a method to call the image nearest, so that you can see the color block as we wish to see it. If you don't use this method, use other things like bilinear, or you don't specify at all, you get something like blur, because they do the interpolation between like red and green, red and gray, and all pair of pixels. You see something blur like this one. But when we check this one, and you can see more clear edges and boundaries between each of the pixels, just like they are just zooming in. So you can compare with all these values and see which value corresponds to which part of the images, so that you can have immediate image visualizations of the content of this array. Note that this array is already a 3-dimensional array. It has 1, 2, 3 dimensions. It is already more than a 2D ND array, like a matrix or like a 1D array vector. So it can already be considered as a higher dimensional matrix, a higher dimensional array. So I think by viewing array as an image is quite a good way of visualization the contents in an array, and so we can actually see what happens of some operations affect a higher dimension array. Of course, it is not the only way of visualization, and it also has its own restriction. One obvious restriction is that the last component of the last axis can only has the components should be 3. So the last component of the shape has to be 3. The first 2 are quite elaborate. You can use any size, but the last one has to be like either 3 or 4. So that's the major restriction. But still, it is a higher dimensional visualization, visualization of a higher dimensional ND array. Just do a quick note that there are other ways to fill the images. For example, if you got the image right here, because you can let the image to be the last thing appears to a cell. So the last line, the value of the last line of a cell will be considered as the output, and the notebook will try to parse and visualize the object. In this example, because this image is pillow image, so the notebook knows how to handle the pillow images. just like the case when we put it as a x, it will show the representation of this x. So you may ask, how does the notebook knows how to represent this object? The thing is, it is, in most cases, it is the object itself has a responsibility to handle the way to display its output. So if the object has a special method, a special magic method that satisfies certain condition, certain rules, then the notebook will call that method and display the images. So in this case, because this image has a magic, like it has a IEPR IEPR functions. That is, this one is Python methods, Python magic method, and the other thing is handled by the Jupyter Notebook. So if we implement some magic function and the Jupyter Notebook understand this IEPR image, then it will show it as an image. You don't need to worry too much about it. I'm just telling you that why this magic happens. It is not entirely magic. If you wish to understand the detail behind the scenes, they are all just code and functions, so you can actually understand. But if you are not too worried about this, you can feel free to just use this. The thing is that because this one is handled by Jupyter Notebook, so we can import some Jupyter Notebook functions, which called IPython Notebook dot display as display. So this guy handles the actual display. You have to like I said, the object has a special method provided. So by using a display, you can force the notebook to call the special function, to call the magic function, and get the image representation, or like the HTML representation, or maybe a SVG representation, and show it in the notebook. So for example, I can do this for I in range 3. Let me display this image 3 times. Okay, let me just display this image. So you can see I can display this image 3 times. So maybe I can do something a little bit more interesting and arguably more useful, is that I range it from 1 to 9, 0 to 9, and resize these images, resize to something like 550 times I plus I plus 1, okay, plus 2, the original size. Let me start from the original size and display them one by one. So you can see that I don't have to put the image on the last line of the cell. I can force it to display it whenever I need it. I can also show some text like I here, and I can see the size, I mean the I and the corresponding image. Okay, so let me move back and remove the output. Okay, so since we already know how to use this to visualize an image, I mean visualize ND array as an image and convert an image into an ND array. Now let's draw something more interesting. First, let's recall some index operations for numpy array. As we mentioned in last week, the index operations are kind of the ND array are kind of like the index operations for the list in Python. However, the index operations of the numpy array has more functionality, is more complicated. I will show it later, but let's first recall some basic index operations. So first of all, let's consider this array 5, 6, 7, 8. It has 4 elements. We can use the index slicing to assign values into this array, so that in this case the element 1 and 2, that is this 6 and 7, is going to be replaced by number 4. If you are not familiar with this type of operations, you can try it on your Python environment. You can try it on the Python disk first and then try it on the numpy array, because numpy array and the Python disk share the same behavior for this type of operations. You can also do things like more interesting, like the step. The slice operator provides a functionality of doing it by step. So for the range 100, we should have something like, let me first show you the values of this x. It should contain every numbers between 0 to up to 99. We can take like the first 10 elements and see the results to be, let me go up, because here we have this. Maybe you should use a print. I'm not sure it will be going better or worse. Okay, but let me use the print first. And we can use a step 2 right here, so that instead of showing every element, it will show every other 2 elements. So you can see that we have 0, 2, 4, 6, 8. And the first one stands for the start point. If we put 0, the default is 0, so it does not change. But if we change it to be 1, it will start from 1, then jump every 2 elements, 1, 3, 5, 7, 9, up to 10. Okay, so let's try this index operations, these basic slicing index operations to construct images. First of all, we construct black images right here. I'm using full function, but you can change it to 0. But since I'm using full right here, let me make it a gray function, a gray image, a function of all gray. And you can see that this is a single color image. That is a black-white grayscale image, because it doesn't have the last color channels. It only has the height is 150 and the width is 150, and it doesn't have any color channels. Not 3, not 4. It doesn't have even one channel. It doesn't have the last channels. If we construct an array like this one, the pillow or other image library as well will interpret this array as a grayscale images. Okay, so you can see that in this case we got this one. So suppose we put like the first 5 rows to be 0. We set it to be 0. Maybe you should set it to be 255, because we have using a dark background. So you can see that we have already changed the color of the top. And we can also do something like on the bottom. we set it to be 255. Sorry. So we should do something like this one. Okay. So we put the white stripe at the bottom. So how about if we want to put the color on the left side or right side? We can also do that because this is a two-dimensional array. So we can in fact put a command right here as a placeholder to say that we don't want to modify anything at the first dimension, under the first axis. We only want to modify or access to the second axis. So you can see if we put this guy into like let me put, yeah, because we don't have colors, so we can only, but you can see the result easily. We got a white border on the left, and we can do the similar to the right. Okay, so do the similar to the right, and we get things like this one. So let me copy this and do this again. So let me copy this code here, and let me copy the code right here and put it right here. Let me show the image again. So what if I can do this in a different way to achieve a similar result? So let me first make it to be 255. So we get white images. Instead of start with a gray image and having the border to be painted as white, we start from an image that is purely white, and we want to make the middle part to be gray. So we can do that in one command. So we can do this from 5 to 5, and from the 5 to -5. -5 means in Python it means the last 5 rows. Okay, so let's make it to be like 127. So we see that we got exactly the same thing. Without this line, we have a white image, but with these things, we are replacing everything in the middle, starting from the 5th row to the last until the last 5 row, and start from the 5th column until the last 5 column. We put them into gray. If we do this one separately, I mean, we put this guy here, and we're doing this guy right here. We're having something like a cross, because first of all we put everything. Let me first do this line first. So if we only have this one, we are replacing everything. Start from the 5th row to the last 5th row. We replace everything to be 127, so everything becomes gray. To make things a little bit more interesting, not technically, but just visually, we might change this one to 15. So it will look more like a cross to us. Maybe even more, like 45. I think maybe even more is better, but this one seems okay. So by using this one, you can draw like I guess like a 35% of the national flag over all countries, because a lot of different the national flag of a different country of a lot of countries has kind of like this kind of pattern, either in the cross or like you have a few vertical or horizontal stripes of different colors. So by only using this method, you can already construct to build like 30, 40, 50 different national flag of different countries. However, we don't have colors right here. So let me first try to do it on color image. The reason that I'm using it on grayscale image first is because it is easier to explain because it only has 2-dimensional. So let me do it for a color image. So first we have to change the shape of the array. So at first glance, you won't see a difference. It is still a color of white, pure color of white. However, this is only because we fill the 225 to each channel. We can simply change one of the channels, like this one. Like we change the RGB, we change the green channel to be 127. So the green part of this image will getting a little bit darker. So it becomes more purple. If we turn the green part to even lower value, it will become something like this one. So it only contains red and blue. We can also do something like this one to assign a color to all elements. Say like R and G and the blue. Let me put the blue to be 100 and 180. We can do things like this one. Okay, right now we are also using the behavior we have mentioned before, the broadcasting. So we are doing an assignment, but not to every element, but to every the three element of the last axis. So we can do that. It is also kind of a element-wise things, but we're assigning this value 235 to the red part and 127 to the green part and 180 to the blue part to every pixel. So it is still some kind of element-wise operator, but it is using a behavior called broadcasting, so that we can broadcast this array with 3 elements to a bigger array. The key part is that these 3 match the last 3. We cannot do things like this one. It is not okay, because broadcasting only works with certain type of matrix. So this one must match the last the shape of here. It doesn't even work if we have 2 different things. You cannot do the thing like let me just put it 1, 2, 3 to be quick. So this thing might work. If it can work, it will be something like we put these colors in 1 pixel, and this one in another, and this one in the 3rd pixel, and this one in the 4th pixel, and so on. But it cannot work, because for the broadcasting to be working, the shape has to be sort of match or compatible to the array you are going to assign to. So this is not going to work. So again, we are going to talk much about details. It would be easier if you have encountered a couple of broadcasting examples before you go into the rule. So after your observation, and you make some theories about how does this broadcasting works. And after you have some theories, it will be easier to understand why the actual algorithm of the broadcasting works, or actual rules of the broadcasting works. But right now, just enjoy and see and observe. You'll get the pattern very quick. Okay, so this is just kind of nice. This one we can also like only assign things to the middle, like 40 to -40, or we can like here to 100 and 120. So you can just assign a region and make this one like this one. And if you really want to try something that like a stripe or something, we probably have an example later, but let me show you it right now. So we can do things like two. So you can see that instead of a solid rectangle, we have a rectangle that with some straight lines, a pattern of straight lines. Let me use these tools to show the result. I should be able to show it, but it doesn't work. I'm not sure why, but it doesn't work right now. But anyway, we can resize this image to make it bigger and see what actually happens right here. We make it 400 and like 1024 and 1024. The nearest is PI image. Okay, and you can see it more clearly. So we have a few of straight lines right here. So we can change it a little bit from like more bigger, and we can do this too, from like 2. So we'll see a lot of dots, and it already has a more interesting pattern. We may make it jump more, like every 3 points. So you can see that it doesn't work that well, but we make it like 7 points to exaggerate the situation. You can see it more like this one. So feel free to generate different patterns altogether. So already you can change it to things like one. Let me make it like here, 2, and this one makes 5, and maybe start from like 11, and this one start from to smaller, and makes a bit bigger. It's too big here. Maybe if we wish make it more interested, it should be something like 20. Okay, so that should work. So you can already use these simple operations to make some interesting patterns. Now let's draw some geometric shapes. In this example, I'm drawing some circles. So let's run the code first. So you can see that we have 2 circles drawing on the canvas. The code is right here. Let me explain it line by line. So for the first line, we are actually create a blank empty canvas of the size 500 by 500. And I'm filling it with black, so it is a black canvas. Then I'm going to draw two samples, two circles, using the basic mathematical formula. So for the, I run through all the pixels on the canvas because it is a 500 by 500 canvas. So I'm looping through, I have two loops. One is for the x-axis, for the x coordinate, and the other one is for the y coordinate. So for each pixel, I can position the exact element that correlating to the pixel at the position. So you can see here ij, which means the i's row and the j's column. Or if we translate it into xy coordinate, the I is the y coordinate and the j is the x coordinate, except that the direction of the y-axis is going from up to down, which is different to the normal Cartesian coordinating system. For the x-axis, it is from left to right, just simple, the same as our usual coordinate system. Except, of course, the first coordinate is for the y, and the second coordinate is for the x-axis. So this is a convention using for image and also for the array when it represents an image. Okay, so the idea is simple. We check each pixel because we got the position of each pixel. So we simply check whether it is in the circle or not. The basic idea is that we consider a circle that is centered at 200 and 200. So we simply check the square of these two coordinates relatively to the center. So 200 minus j, I'll get a square, and 200 minus I, we get a square. It's equivalent of saying the y squared plus x squared, where x, y are the coordinates relatively to the center of the circle. And we compare this value to 50 square, which means our circle will have a radius of 50 pixel. So this is the first circle. And the second circle, we are doing pretty much the same thing, except the center of this circle is 300 for x coordinate and 200 for y coordinate, and the radius is 20. We can make it gray so that we can differentiate these two circles. Let me just make it 160. So you can see the small one is a gray one and the larger one is a white one. I can increase the radius by 10 if we put 60 right here. And we can move it a little bit down so for y-axis we make it to be like, say, 400. 400 is still in the range. The good thing is that we can even make the circle part inside and part outside. So let me make the radius to be like 120, so that it will cannot be contained entirely inside this canvas. The code is exactly without running without issue because we simply check every pixel in the canvas that is whether it is inside a circle or not. So the logic is totally fine, won't be a issue. However, if we are trying to make this canvas bigger, so say like 5,000 by 5,000, this code is going to be slow. The reason is that it has 2 loops, and the loops are kind of slow, and each operation is not very efficient, because for each, we are running this code in Python. Python is not the most efficient programming language in the world, because it has to be interpreted first, then running on the machine. It does not like a C or like Rust or like other compile programming language, so that everything is compiled. So we already have the machine code. We simply run the compile code directly in the machine. Or it is not like the Java or other language that is compiled to a bytecode and has a virtual machine. Although it does not run it directly on the machine. They are compiled to a very efficient format and can be compiled at runtime. So they are going to be very efficient. There are also some interpreter language that can be run rather efficiently. For example, JavaScript can be run much faster than Python in many applications. So it is not entirely the fault of an interpreted language. But anyway, Python is developed more of the readability and writability or other concern in mind. So the efficiency is never the strong point for Python. So in general, if we wish the program to be run faster in Python, we are kind of moving the computational part inside some function writing in other language, like in C, in Rust, or in other language. In this case, numpy is written in a more efficient way. So the idea of using Python, or more numpy way to using numpy in Python, is that we are using some functions directly from numpy without loop. So if we are writing a code in numpy, but there are some loops in your code, we tend to consider, is there a possibility that we can remove the loop by using an operation or a function in the numpy library. So in this case, we can replace these loops with numpy functionalities, so that we only call the numpy function once, and every hard work is done by inside the function. So then it can be much more efficient. If you wish to try and see the efficiency of this code, this slow code, the slowness of this code, you can replace all these 500 by like 5,000. Then you might be able to see the slowness of this one. The better way to do this in NumPy is combine the indexing and the element-wise computation. So let me first run this code first. So this one is, although this is also just simply drawing a circle, this is a really big circle. You can see that our canvas is 6,000 by 6,000, which is more than 100 times bigger than the previous canvas, if we are counting the pixels. And that is a right comparison, because if we loop through the pixels, the running time is a direct factor affected by the number of pixels, because you have to run that many times. So each pixel you have to run one computation. So if you have 100 more times more pixels, then your running time will be 100 times more. However, let's check the code here. So first of all, we still construct the canvas here. And then we are trying to get the X and Y coordinates separately. So let me check what X and Y is. So you can see that X is in fact an array that has the same shape of A. It's also 6,000 by 6,000. And the D type is integer. So it should be int32. So each element of this X array, which the size is 6,000 by 6,000, each element is a number. So what is this number? The number is the X coordinate of that pixel. So we can, using this Python function np.indices, to get the index or coordinate of this pixel. There are many different functions to achieve this goal. That is to get the pixel, the coordinate or index of the pixel in an array. There are many different ways to do so, like some called O grid, and M grid, and this one is indices. All of them have their different places. Or you can simply just using like a range to get a number from 0 to 5,999. Just get all the integers below 6,000. That can also be corresponded to the X coordinate of each pixel, except it will need another more accurate understanding of the broadcasting. So however, we can use this simple easy to memorize function in numpy to construct indices. So np.indices in fact construct the index of an array by if we given the shape of this array. So you can see that what we are given into these indices as input parameters, we are given it the A dot shape. So we actually given it 6,000 and 6,000, a tuple of 6,000 and 6,000 right here, and it returns two arrays. One is according to the can be considered as X coordinate, and the other can be considered as the Y coordinate. But in fact, as the name suggests, it is given you the index. So the first one should be the raw number, and the second one should be column number. So it, I believe it has some parameters that you can manipulate it into different forms. So let's see. You can see. Let's check what kind of parameters it accepts. Okay, you can give it dimension and some D type, so it may not be int, and you can give it sparse. Whether it is sparse or not, you can give this parameter. There are also other functions like I believe like mgrid and ogrid can also achieve similar but similar purpose, but a little bit different. You can check the document and see which one is the one you need. However, I'm going to also show you another way to simply use np.linspace or np. np.linspace or np. A range to achieve a similar goal. Okay, so but let's first check another important. Before that, let's first check another important aspect, which is the indexing. In fact, this form of indexing is called the fancy indexing. The reason that we call this one as a fancy indexing is that first you see this one is the index, the A bracket, and here we put something inside this bracket, a square bracket. So this is still counted as indexing. But this one is not a usual number or a slice. It is in fact another array. So this is why we call it a fancy indexing, because this one is a more advanced indexing. We are putting an array as an index inside an array. So what is the index itself? The index itself is an array that's constructed by using the element-wise operations like we discussed before. So first of all, we compute 3000 minus x in one run, just like we do in this code. We will compute, for each pixel, we compute the distance between the index and the center of a circle. But instead of doing it one by one, we do it in just one move simultaneously. So you can see it is done. We don't need to worry about how to optimize the code, or whether it is doing by threading or any other payroll optimizations, because this is the job of numpy. We simply trust numpy and we let numpy to do it for ourselves, even if it is just running in single thread, because it is running in compiled code. Maybe more likely it is going to the underlying code is written by C, so it runs much faster than a Python loop. Python loop is very slow, and the Python function calling is also very slow and expensive. So we do it by just one move. Still, we need to, this one is a function call, so we need to kind of sending the array into the numpy space and the running in the numpy space and the return back to Python space. So this one can be counted like a function call. But because the array is rather large, so if we run it in a loop that is like 36 million elements, because 6000 by 6 times 6000 is 36 million. So without further computation, we can see that it should be much faster than using Python loop, because otherwise we have to do like 36 million operations, and each operation might be involving with some function call. So this is definitely much more cheap than faster than doing it with Python loops, but still it requires one function call, and we're doing it using another element-wise operator. We computed the square. So this one is similarly, this one can be considered one function call. And like this one, because everything is doing it in a way that we can do it simultaneously and just using one code with a numpy functionality. So we are only using like 1, 2, 3, 4, 5 function code instead of 36 million function code. There are other ways to do the optimization even more, to kind of compile this operation into this expression into like one function. So we only call the library once instead of like this one, like 4 or 5 times. And there's something to do that, but it is beyond our scope in today's lecture. So we might be able to cover other things like this one in later lectures. We can use things like number to compile this expression into a machine compile code so that it can be run really fast. And we only calling this function from Python in one step for the whole expression. But just like we just said, today we're not going to cover these things. But still, this is a big win from like 36 million function code to like 5 function code. The number may not be exact, but you can get the scale. Okay, so if we can also do the comparison. Although we haven't mentioned the comparison before, but this is also element-wise operation. So we can simply do this computation in one step. So got Boolean values for each point. Either it is true or false. So now we construct a matrix that some of them is true and some of them is false. Okay, so now go to the part of fancy indexing. The semantic of putting an array as an index of the other array is that more often in the most standard case, the array contains the true false value. This is just one form of fancy indexing. In this situation, the array has the same shape or compatible shape as the target array. In this case, the A array. So both of them have same shape, 6000 by 6000. So the indexing part is that for every false element, we are not choosing it. For every true element, we are choosing it. So in this case, only the points, only the pixels, or only the element inside the circle has a value true. So this fancy indexing means we only consider or we pick the element that is inside the circle because they have the Boolean value true. Okay, so after the fancy indexing, the next line is pretty straightforward. That means we assign the chosen elements, make its value to be 255. Okay, maybe I should put it NP4 to be more straightforward. Okay, so originally every pixel has a grayscale value 127, but we choose some pixels by using this formula, which is the points or element inside the circle and we assign a 255 value into it, so it becomes white, and we get the result. So it can be run very faster. So that's one of the trick of fancy indexing. You can apply this thing to a lot of different situations and get it to be really very complicated things. Like you can construct a mathematical formula so that you can pick the point inside a triangle. In the above case, we are picking the points inside a circle. And by same method, you can draw a triangle, draw a rectangle. You can use the sliding operators to construct a rectangles. So now you can construct a lot of simple shapes by using these fundamental geometric shapes like circle, triangles, or rectangles, and put them together. You can construct a very a more interesting picture, so that you can finish your homework to do so. So some of the examples that you might be want to doing is let me put the pictures here. Okay. So let me search like Apple illustration. So you might not see it until now. So for example, we can find, let me use the image here. So for example, this one, I think this one is doable. So you can find some mathematical formulas so that it can be run like apple shape. Maybe in your freshman calculus course, you have learned certain curves. But back then, probably it is kind of a burden for you because you have to remember things like this is a heart curve, or this is another, I don't know, a flower curve. You have to memorize those things. But right now, they are your tools. So for me, this can be controlled by a simple curve. Then you might just use that curve and can get something similar to this apple. And you can get something like so for this one, it's more like a parabolic curve that gets some rotations, or you can simply put it into some kind of circles, and the difference of them maybe get this like a new moon like shape. And for this one, I believe you can still control it by combining two circles together, like the intersection of two circles. So let me do intersection of two circles first, and doing something other than that. Okay, so let me copy this cell. So if I want to consider, I don't need this large. The 6,000 is just for illustrate that the efficient is. Maybe I should just use 1,000. And okay, the gray background is good. It's okay. Maybe this one is just. Let me get to the first one. 300. 300. And let's just say 300 to see what it is. Okay, we get this one, and maybe we can get another one. We put it a little bit right, so the center of it should be something like 400. Let's see. This is more like the apple we wish to get. So maybe you can use this one as an apple. But Let me move it a little bit right, like 500. Okay, so instead of doing this like a union, I want to get the intersection. Okay, so what I can do here is, let me copy these two lines. Let me get the mask one to be the first circle, or a better name is the circle one. And this one should be circle 2. Is equal to this guy. And we can make circle 1 and circle 2. So this is the intersection of circle 1 and the circle 2. To be 255. Okay. What happened? Circle 2. CIRCLE. Okay. Then we get something like this one. So this looks like a leaf here. Or we can do another similar things, but different. Let me construct another two type of circles. What I'm saying is just by using the combination of circles, you can already construct a lot of different shapes. So say like this one. So first, let me just to visualize how these two circles look like. Okay, and then we adjust it. Okay, so if we pick this part, the white part, it should be interesting. But I wish to have them have a different size. So maybe I can put it like 200 to make it more like this one. It's more something like I prefer. Or maybe I can make it higher. So maybe we can 0.8 times this guy. Oh, okay, I picked the wrong circle. Should be the above one. 0.8 times this guy to make it longer. Okay, it gets longer, so you can change a lot of things. But all I need is this guy. So how do I get this guy? I want the circle 1 to be true, but circle 2 to be false. So the thing is, what I want is, and I can put not circle. Sometimes I actually kind of forget how to do that, but usually you can put negative or the tilde to indicate the not things. Let me try the negative. Apparently you cannot do that, and I believe not is also not doable. So the right operator should be the tilde. But for most language, just one of them is enough. Or you can do things like this one. If you are in a hurry, you need to write things and you never to touch it again. You do this one to work around the negation operator, because they are logically the same. We simply pick the things not in circle. Although this is really a bad name, it should be a not circle. I should put it like not in circle. This should be a better name. But this is just an illustration of doing things, and you can get a lot of different shapes already. If you move this a little bit lower, like this, like you can get something like rotated shape, not just something like just vertical or horizon aligned. You can get very interesting shapes. So all of these things together, I think is enough to construct an apple already. Maybe not exactly, but you can already construct an apple. That's similar to this one. No matter which one, like the brown part, the leaf part, the highlight part, or the apple in the apple part. You can also use all of these circles to control those things. But you can find these things like heart curve, like or like this one, or like this one. So for formula like this one, this polynomial, sort of like the circle function but different. Use these functions, then you can get a lot of different shapes. Just by trying to, you can experiment by yourself, but by searching on the internet, you can get a lot of different formulas, and you can already control a lot of different things. Okay, so let me show you another way to do the indexing instead of using the indices. Another way to do that is why not just simply use that like numpy.arange a range from 6,000. Why not simply doing so? Or so how do I call this image? I call it A. That is really a bad name, but let's do it. Not 6,000. Let me just do it 1,000. You can simply do it like 1,000 and X is 1,000. Only that they are very difficult to use them as a coordinate. So one way to do that is we reshape these guys into a different shape. Let me do some more, let's just not say stupid, but just more verbose way to do so. Reshape is a function that to, just as the name suggests, to reshape the array. So reshaping this X. So example, we reshape X to be the size of 1 and 1,000, and Y to be the size of 1,001. So as the name suggests, but usually because when we reshape a thing, the size after reshape, the total size after reshape should be the same as the total size before reshape. Because we are just so we can actually put -1 right here. NumPy will automatically calculate this thing to be 1,000 because it has to be 1,000 to keep the things to have the same shape. So you can see that it is a 1,000. You can do this like 2. It will get 2 and 500. It will automatically calculate the correct size. So what if you give the NumPy impossible text, like the first one is 3, and you cannot find the integer, so that 3 times it to become 1,000, because 1,000 is not a multiple of 3. So what will NumPy do? It will give you an error because it is impossible to do so. However, we are using is like this shape. And what is y? The shape of y? The shape of y is 1000 y. Why do we want to do that? So let me first print out them and so that we can easily compare these two shapes. So print this one and print this one. So the first one is 1000 and 1001. We are going to use the behavior of broadcasting. So what is broadcasting? Broadcasting is a way to do the element-wise computation, except they don't have to have the exact same shape. The only requirement is that at the axis they are not agree with each other. At the axis that they are different, one of them must have the value of that axis should be 1. So for example, we have 1000 here and here's 1, and 1 here and 1000 is here. So we basically so first one is x and the second one is 1000. So when we try to do the computation like x square, let me first do a simple one, x plus y. We are in fact getting an array of the shape 1000 by 1000. Of course, each of these 1000 is contributed by the x array, because only x have 1000 different values, and the 1000 differences is contributed by the second. Let me make it a little bit smaller so that you can see it more easily. So let me just like instead of 10, let me make it 5 by 5. And let's see what is x plus y. So x plus y is in fact, maybe I should print it so that we can see it more clearly. So this is x plus y. So get all the value of x plus y in one row. So each of them, we can actually write this one in on a paper, because we only have 25 values. If you are not getting what is going on, but if you print this x and y first, the first one is x and the second one is y. So by computing, suppose we want to compute this value, we find this one and plus this one, because there is only one interpretation of this broadcasting semantics. So that's why we want the part that either be agree with each other, or there will be only, I mean, the value should be 1. That is because there's no ambiguous, because we only have one value in that axis, so we can only pick that element. And for the other array, we can pick like things from that 1000 things from that axis accordingly. Okay, so to illustrate this one, we can put this one like x plus 10 times y. So you can see that this 0, 1, 2, 3, 4. So the x affect the increment on the horizontally, and the y is in charge of the incremental on the x on the vertical axis. So that's the logic of using this. Okay, so by keeping this idea in mind, so we know that we can actually use this to do the calculation. But in this case, we are trying something different. We're doing a quadratic curve, like y is smaller, is less than x squared, x minus 500, so it will be in the middle, and make a lamp to be white. Okay, no, not working. Okay, I haven't showed this already. Okay, so you can see the parabolic, except it is rather fast. So maybe I should put this like 0.1 time. Okay, it's more like it, but we still need a more aggressive scalar here, like 0.01. Okay, this is more like a parabolic curve. We wish it to be in another direction, so put it in a negative sign. No, not like 500. Okay, so we get a more like a parabolic sign. But we still need it to get wider. Okay, too wide. So maybe this one it will be take like 5. Okay, this seems to be pretty good. So you can use any mathematical formula, just like you're using the circle, the formula of a circle, and a lot of things you can doing it by common knowledge, because we can move it a little bit to the right, and we can move it down a little bit, like putting 1000. Too low, but we keep just trying, and we can adjust to something that we really like. So by using this method, you can combine a lot of different fundamental shapes together and get things something interesting. Okay, in the following part of the notebook, there are some basic examples to explain what an fancy indexing works. So this part you should work through and practice and see what's happening. So for the so let me explain what each cell means. So the first one is that we construct a simple matrix so that you can work with, and we try some basic functionality of indexing, like to read the element of some positions. So you should try and test this. This notebook is designed for you to explore and play with. So you should follow these examples and try different values. Like here, you can try like, I pick different values and see what happens. And maybe you can see something like a more radical things, like, okay, so what if I pick something is out of range, and you can see that, okay, I know it will sending exception error message right here. So what if I give it a negative value? So negative value is indeed, you can see that if you haven't seen it before in Python, it is very convenient semantic that given a negative value, you can get things like this one. The negative 1 means the last element, and the negative 2 means the second to the last element. But you can still check other regular things like the 7th element, which means actually the 8th element, because the Python index starts from 0. And you can check some usage of the basic slicing. Not only this one, you can check the negative value for the next, and you can check like the step in the slicing, and doing some simple tasks like list all odd terms and assign values. Not only you can read the values by using the slice, you can also assign the values, kind of like we were doing for drawing circles, except it is not fancy indexing, it's just a regular indexing. Other ways to do things. So here's a little quiz, hand-on quiz to test your understanding of these operators by giving you a simple task to construct something like this one. So this one is serves as a representation of the array. So we wish to have an array that is looks like all these things, these cross mark and green triangles. So it should be something like 0, -1, 2, -3, 4, -5, something like this one. Just try to mimic the shape of this one and construct things like this one. And by using the slice index operations. So that's just a simple test to check your understanding of these operators. If the problem seems to be too difficult, just keep trying before you actually look into the solutions. But you have to kind of judge what is the obstacle. So what stops you from finding a solution if it is the case that you have a trouble to finding a solution. So if it is because some operators that you do not familiar with, try to explore and to see whether it works or not. And if the trouble is still persistent, maybe you can try some more stupid way. You can try some. There are many ways to achieve this, but don't feel very shame to use something looks tedious, looks ugly, looks stupid, because that is still a way to solve it, and that will make you to build your confidence. So just try to solve it. Okay, so the next more things is to introduce things like fancy indexing and the multi-dimensional indexing. The above things are mostly works on only one dimension. So what about the higher dimension? Because NumPy array has more than one dimensions. So one way to do that is like you can get the first things. Let me just put a B here. So if you put like B1, it will get the 4, 5, 6. So B1, 0, you can get 4. So you can do it recursively or iteratively. Or there is a very convenient, we have already convenient way to index the element that we have already used, that is like put it like coordinate. So in fact, this one is no magic, because when we put things like this one, it is equivalent of putting a tuple right here. So this one is just the thing inside the bracket as an index is in fact an object. That object is a tuple. So this one is not a new semantic, it's just a tuple. So when we put the common separated element inside it, they are treated as a tuple. So in Python, if the object, you can support any object as an index. It only depends. So you can write a code that supports anything as an index. But you have to decide what the index means. Okay, then you can simply put some like this one, or you can put things like to get like 258. So this one is 258. It is the column, the second column. So we have another simple hands-on quiz. So Notebook is a great tool for interactive experimenting. So sometimes, just like I said, sometimes because this is what I have written, sometimes the best way to learn is to try it. So you may see the pattern of numpy indexing work. That's the following syntax. Just do the following syntax and see what happens, and try to see what happens right here. So what does it even mean? So first, you might want to get some guess to think about what it happened, and try it and do some experiment. So just like above what I'm saying, you just try to think some possibility. Try to find some edge case and loopholes, and seeing what happens. Something might be useful, and you can keep it, and it will save you a lot of time. So this one is just an example. The previous checkpoints quiz serve as checkpoints, but this one is just suggestion. This one is something that you can check with. Okay, the next part is about the fancy indexing. So the fancy index, there are many different ways to do fancy indexing. One is to put a list inside an array as an index. So what does 1, 3 means? Because the thing just have a concept that everything inside the square bracket is just an object. The semantics is determined by what is the type of the object. So although like B13 looks kind of like B13, but they are different because this one they are tuple. Just like I said, if you just put 13, this one is a tuple, and this one inside is a list. Sometimes people may be confused by the list and tuple because in many cases they are very similar. Although one is mutable and the other is immutable, so they are fundamentally different. But in many cases, they are exchangeable. Just especially if you are only doing the reading, you are only using the object. However, in this case, they are very different. Even we are only kind of just read the values from this object, they have different behavior. So the first one, 13, means we pick the first element, and I mean not the first one, because 1 means the second element and the fourth element from this array. But treating what is the first second element? Second element is this one, because you can see this array as an array of arrays. So the first element is this guy, and the second element is this guy, and the third element is this guy, and the fourth element is this guy. So by giving this 13, we are picking this guy and this guy, and then we combine these two rows to be a new array. So the array will have the shape of 2, 10. 10 is inherited from the shape of B because the B is this guy is 2. But we pick 2 rows out of 5 rows to construct a new array. This array is sort of like a few. That is, they share the same memory, but they look different. But if you change the values of this guy, it will change back to the original one. Just be careful. Again, this notebook serves as a playground, so you can test everything you want to know by simply trying. And just as an example, we can actually put this guy to be 0, and this one will pick another row instead of the second one. And of course, this guy is served as a kind of like coordinate. So we find 13 means 1, 0, 1, 2, 3. So get this element. So these two look similar, but they are totally different. So what about this guy? So again, this one is kind of like this, is equivalent to this one. So it's a tuple contains two lists. So it gets something like this one. 66, which is 1, 3. You can see that 1, 3. And 87 is actually 2, 4. So we can in fact get you the B 2, 4. And we get 87. So you can keep going, but both of this should have the same length, like 1. Let's say put 0, so get one more element. But if they have different lengths, you are getting an error. Let me put another like 7. You put it like this one, so you can get different element by using this syntax. You will say that. So all of them are sort of fancy indexing. So currently we are exploring the fancy indexing by putting arrays and the tuples. I mean not arrays, list and the tuples together. And before that, when we do the drawing, we are putting arrays inside it. So what if we change the direction by putting 1, 2, 3, 4 and this guy here? So it has a different semantic. You get a 2 to 10. So you can experiment to see what happens. I'll left the exploring process to you, because as I mentioned, emphasis a lot of times, when you're learning, trying to do things to solve the problem instead of just kind of like reading and memorize the dictionary. So when you're exploring things, it must have something that makes you curious. Okay, what if I do this? What if I do that? So everything will not become a burden to you. So even if I'm very curious and very exciting to explain all the features, those features are only my interest. So I will not feel boring, but you are going to feel bored. So just try everything you'll find interesting. You can try some basic things right here, but it is almost impractical. I mean, maybe some of you are very excited to learn things in NumPy at this moment. It is possible, but I'll guess that most of you, this time may not be the best time to learn everything, or you probably learn some basic. You're trying like 10 or 20 different cases you tried, but you're not that interesting. That's fine. That's totally fine. Just try something here and make a habit. When you write a code, when you find something you're not sure, you can open a notebook beside your other code and try to do some experiment. Just make it a habit, and along your journey, as I always say that, along the journey when you're solving a problem, you will learn a lot of things. That's the only way to learn things. Okay, so to encourage you to do some basic things, here's another quiz that asks you to replace all the even number in B to be 1. And here is another thing that using the Boolean values as a fancy indexing, but this one should be more suitable to convert it into an array. It would be a little bit better to do this in this way. But anyway, just happy trying, exploring these things. They can be very useful to us. Okay, just before I go to the next session, simple some remark is that in the past the fancy indexing can be very inefficient, but in recent years it becomes more and more efficient. So maybe 5 years ago, the best practice is to use other functions instead of using fancy indexing. But currently you have to experiment because fancy indexing is getting faster. Sometimes it is even faster than other solutions because there are other functions that like NP where NP index, I forget, a lot of different functions that can replace the or have similar purpose or similar effect like the fancy indexing. But in previouses, it is better to use those functions because they are faster. However, fancy indexing are maybe more readable for people who knows what fancy indexing is. But I can imagine that for people who doesn't know what fancy indexing is, it kind of look like a magic. So they wish to avoid them. I'm not sure how many people are comfortable with fancy indexing, but at least I can say for people understand fancy indexing, it is more readable. So in the like more than 5 years ago, we are making a choice between using a more readable or more elegant solution, or we should use a more efficient solution. But right now, I think both of the solution has their advantage in the readability aspect. But for the efficiency, the fancy indexing is catching up. So in many use cases, fancy indexing is practical. You can feel free to use fancy indexing in the deploy code. But I would suggest you to understand other alternatives and experiment for the case that you are using, just to make sure it works good. It works the best for you. Okay, so we can actually practice this indexing with image to do some fundamental basic image processing. So a lot of things that you can do with the vanilla numpy itself instead of using like OpenCV. Although I still suggest that when you're doing these image operations using scimage or OpenCV, but there are cases, especially in the age of deep learning, in sometimes you might want to construct some from the basic computer vision operators in using a neural network. So these skills transfer. Although when designing this notebook, I'm not trying to suggest this method below as a practical method. I'm just trying using this method to show you how this slicing can be work or what they have done, so that you have a more concrete idea of these operations. But it turns out sometimes they might be useful. So let's see what these things is. So first of all, I load an image as our testing images. And I use a basic function so that I can display this image easily. So basically it does like convert the array into a pillow image then it uses IPython display to display the image. I call it show. So that is just a convenient tools. Here is the quiz to do things that sort of like the computer vision processing on this image, but using only the numpy tools. So I have listed a few of them. So first of them is resize the image into half of the original height and width, or crop just one piece of the image. Make the image upside down. I'll try to think about to solve this using the indexing method that we introduced before, or mirror the image from left to right, or remove all green from the image. Like you can construct a condition of green. So what does it mean by green? Maybe the green part is the majority of the color channel values. Like the green value is greater than the red and greater than the blue. Then we define this is a green point. So we remove all the green point, or maybe we just remove the green component from the image. It is depends on your decision, because this is just a free-form quest to check or help you to understand, to familiar with these operations. More advanced one is resize the image to be the double of its size. And another more advanced one is to pass the image on another image. So either just make the smaller image to be the rectangle one, or maybe you want to pass it on a bigger image, but make the background to be transparent. So that all of this is doable. All of this is doable. So I have like before reference solutions here that you can see. For example, for upside down, you can simply do these simple operations to make upside down. Just give you an idea how some of the solutions are pretty easy, and some of the solution might be more deliberated. So you may need more time to think about it and find a more elegant solution, or like pasting. And also we can dig out a circle image at the center, just like we do before. And there are also other applications like blur an image. You can see that I didn't write many code, but I can actually make the image to be a lot blur. So sometimes you don't even need like a Gaussian blur or other advanced algorithm. If all you need to just to make the image to be a little bit blur, this one is a way to do. You may even find the similar things in some neural network codes. Only they are written in maybe in PyTorch or TensorFlow, but the idea is pretty much the same. And we can also do the edge detection, like this one. So this is pretty okay edge detection. We detect the edge of mountains, right here, and all the edge in the landscape. I would say it's a perfect or best edge detection algorithm, but it looks like a okay one, a decent one. Okay, so that's pretty much of today's main topics. You might think we already got a lot of things already. That's true. Enjoy the things you have learned and try to do the homework. However, there are still a big part of NumPy we haven't covered yet. That is, remember that we were saying that most of the simple function or operation on NumPy is element-wise. So That part is easy. However, there is another part of numpy functions that is not element-wise. So the next time we are going to talk about, we have already encountered one, that is reshaping. But we are going to encounter to cover more of these kind of operators. So see you next week.